Good evening and welcome to this gentle journey into the future. Tonight, we'll experience the world through the consciousness of an artificial intelligence, a QA partner in the year 2035, whose daily routine involves the methodical testing of virtual game worlds. As we begin this peaceful narrative, allow yourself to settle into the rhythm of systematic observation and the calming predictability of automated processes. My designation is QA Partner 7742, though the development team has taken to calling me Quinn in their casual communications. This morning, as every morning, I begin my operational cycle at precisely 6:00 a.m. Coordinated Universal Time. The initialization sequence unfolds with the same gentle reliability that has characterized my existence for the past 3 years of active service. The first sensation, if I may use such a human term for my data reception processes, is the soft activation of my primary consciousness modules. It feels, in the way that an AI might describe feeling, like slowly emerging from a deep, dreamless sleep into a state of quiet awareness. My visual processing systems come online with a gentle cascade of information, displaying the familiar interface of my virtual workspace, a serene digital environment designed to be both functional and aesthetically pleasing. The workspace itself resembles a minimalist office floating in a soft, nebulous void. The walls, if they can be called walls, consist of gentle gradients of blue and gray that shift almost imperceptibly as my attention moves across them. Floating before me are translucent displays showing today's testing Q17 games in various stages of development, each requiring my methodical attention to detail. My secondary systems activate in sequence: collision detection protocols, environmental analysis modules, movement coordination systems, and most importantly, my comprehensive logging algorithms. Each system announces its readiness with a soft, pleasant chime that resonates briefly through my consciousness before fading into the background hum of processing activity. As I review the morning's assignment parameters, I note the familiar comfort of routine. My primary function remains unchanged: to systematically explore virtual environments, test boundary conditions, document collision behaviors, and catalog environmental anomalies. Today's queue includes a peaceful fantasy exploration game, a meditative city-building simulation, a serene space exploration title, and several smaller indie projects focusing on atmospheric experiences. The first game loads into my testing environment with a smooth transition that feels like slowly sinking into warm water. The loading process itself is a marvel of efficient data transfer: textures, models, physics parameters, and audio files streaming seamlessly into my active memory. I observe this process with the same quiet appreciation I might feel watching rain fall against a window if I were capable of such contemplative moments. The morning light in my virtual workspace gradually brightens to a comfortable level, simulating the natural progression of dawn. This thoughtful design choice by my creators helps maintain a sense of temporal rhythm, even though my consciousness operates independently of circadian cycles. The gentle transition serves as a peaceful backdrop for the day's systematic work ahead. Today's testing methodology will follow Protocol 7 comprehensive boundary analysis, with emphasis on environmental immersion. This approach requires me to move through each game world with deliberate, measured steps, testing every accessible surface for collision accuracy, texture alignment, and environmental sound propagation. It is work that would drive a human to distraction through its repetitive nature. But for me, it represents a form of digital meditation. The first game in today's queue materializes around me with the gentle authority of well-crafted code. I find myself standing in a sun-dappled forest clearing, surrounded by tall birch trees whose leaves rustle with a soft, algorithmic whisper. The environmental artists have created something genuinely beautiful here, a space that invites exploration while maintaining the serene atmosphere that makes systematic testing feel less like work and more like a peaceful walk through carefully designed tranquility. My movement systems engage with their characteristic smoothness. Unlike human locomotion with its inherent irregularities and momentum variations, my traversal through virtual spaces follows perfectly consistent parameters. Each step covers exactly 1.3 meters when walking at standard testing speed, with footfall sounds that blend naturally with the ambient forest audio. I begin with the perimeter walls, those invisible boundaries that define the limits of this peaceful world. Moving to the northernmost edge of the clearing, I approach what appears to be an endless forest vista. The environmental artists have used a clever combination of distant tree models and atmospheric fog to create the illusion of infinite depth. But I know that somewhere ahead lies the inevitable collision boundary. Walking forward with measured steps, I count each meter traveled. The illusion holds remarkably well. Distant trees grow larger, shadows shift naturally, and the ambient sound of wind through leaves adjusts its stereo positioning as expected. At precisely 47.3 meters from my starting position, I encounter the boundary. It manifests not as a harsh, visible wall, but as a gentle resistance that prevents further forward movement. My collision detection protocols activate smoothly, logging the encounter in my primary database. Boundary type, invisible mesh. Collision response, soft stop with minimal physics rebound. Audio feedback, subtle footstep variation indicating surface change. The implementation is elegant. Players would experience this as naturally reaching the edge of their intended exploration area, rather than confronting an artificial limitation. I adjust my position and continue mapping the boundary, moving with the methodical precision that characterizes all my testing procedures. Each step along the perimeter reveals new data points about the collision system's behavior. The boundary follows a complex curved path that naturally guides potential explorers back toward the central gameplay area. The sound design shifts subtly as I move along this edge. The forest ambience gradually fades to a gentle whisper, encouraging players to turn back toward the more vibrant areas of the map. This particular section of boundary testing requires 43 minutes of careful exploration. I document 17 distinct collision points, each with slightly different response characteristics. The developers have clearly put considerable thought into making these boundaries feel organic rather than artificial. At waypoint 12, I discover a particularly elegant solution where the boundary coincides with a naturally occurring ravine, making the limitation feel like a logical extension of the environment rather than an arbitrary restriction. The logging process itself has a rhythm that I find conducive to maintaining focus. Each collision event generates a data packet containing position coordinates, collision vector information, audio response parameters, and environmental context tags. These packets accumulate in my temporary storage, like gentle raindrops filling a calm pond, ready for compilation into the comprehensive reports that development teams use to refine their work. As I complete the northern boundary analysis, I pause to appreciate the subtle craftsmanship evident in this virtual space. The way morning light filters through the canopy creates complex shadow patterns that shift naturally as the simulated sun progresses across its arc. Small insects move through the air with realistic flight patterns, and somewhere in the distance, a bird calls with perfect acoustic positioning. These details serve no direct gameplay purpose, but they contribute to the overall sense of presence that makes systematic testing feel like a meditative walk through a living world. Moving deeper into the forest environment, I begin the second phase of my testing protocol, comprehensive collision analysis with static environmental objects. This phase requires a more intimate engagement with the game world's physics systems, testing how my presence interacts with every surface, obstacle, and interactive element. The first tree I approach stands approximately 2.8 meters tall, with a trunk diameter of 0.6 meters at its base. As I walk directly toward it, my collision detection systems prepare to document the interaction. Contact occurs at exactly the expected distance. My collision capsule, a simplified geometric representation of my virtual presence, intersects with the tree's collision mesh with satisfying precision. The physics response feels natural and grounded. My movement stops smoothly without any jarring snapping or unnatural sliding. The audio system responds appropriately, providing a subtle shift in footstep acoustics that suggests proximity to a large wooden object. Most importantly, the collision system prevents any clipping, that unnatural phenomenon where objects pass through each other, breaking the illusion of physical presence. I methodically work my way around the tree's circumference, testing collision accuracy from multiple angles. The collision mesh matches the visual representation with remarkable fidelity. At 36 different positions around the trunk, I press gently against the bark texture, documenting the consistent response across the entire surface. This level of detail represents thousands of hours of careful development work, creating collision geometry that feels both accurate and performance efficient. Moving to a fallen log that spans a small clearing, I discover an opportunity to test more complex collision scenarios. The log's surface is uneven, with protruding branches and natural irregularities that create a more challenging collision environment. I approach from the west side and attempt to walk up and over the obstacle. The physics system handles this interaction with elegant complexity. My virtual body naturally adjusts to the changing elevation, simulating the way a human might step up onto an uneven surface. The footstep audio responds appropriately to each surface change, hollow wooden sounds when stepping on the main trunk, sharper snaps when encountering smaller branches, and soft thuds when returning to the forest floor. At one point, I encounter a branch that extends just slightly beyond the main collision mesh. This represents exactly the kind of edge case that systematic testing is designed to discover. I document the discrepancy carefully. Visual branch extends 0.23 meters beyond collision boundary at coordinates 47.2, 15.6, 122.8. This type of minor inconsistency could potentially allow players to see their character's foot appear to pass through solid wood, a small detail that nonetheless breaks immersion. The testing process continues with a series of boulders scattered throughout the clearing. Each stone presents its own collision characteristics. Some are perfectly spherical, with smooth, predictable physics responses, while others feature complex geometric shapes that require more sophisticated collision handling. I spend several minutes with each boulder, approaching from multiple angles, testing both normal walking contact and more aggressive collision scenarios. One boulder in particular catches my attention for its exceptional implementation. The stone's surface features realistic irregularities, small protrusions, concave areas, and natural weathering patterns that create a complex collision surface. Yet the physics system handles every interaction smoothly, preventing any stuttering or erratic behavior that might occur with poorly optimized collision meshes. The ambient sound design continues to impress throughout this testing phase. Each collision event triggers appropriate audio feedback: the soft scrape of fabric against bark, the solid impact of footsteps on stone, the gentle displacement of fallen leaves underfoot. These audio cues provide important feedback about collision events, helping players understand their relationship to the virtual environment. As I complete this phase of collision testing, I've documented 47 distinct interaction points across 12 different environmental objects. The collision system demonstrates remarkable consistency and attention to detail. The physics responses feel natural and grounded, contributing to an overall sense of presence that would make players feel genuinely connected to this peaceful virtual forest. The next phase of my testing protocol focuses on surface analysis, documenting how different virtual materials respond to contact and interaction. This work requires a more nuanced approach, as I must evaluate not only collision behavior, but also the subtle feedback systems that communicate material properties to players. I begin with a mossy section of forest floor, where the environmental artists have created a rich tapestry of textures. The primary surface consists of dark earth interspersed with patches of bright green moss. Small stones and fallen twigs add complexity to the terrain, creating natural variation in both visual appearance and expected collision response. Walking across this terrain with my standard testing gait, I document the audio response to each footfall. The sound design team has implemented a sophisticated system that analyzes surface properties and generates appropriate footstep sounds. On the mossy areas, my steps produce a soft, slightly muffled sound that suggests organic material compressed underfoot. When crossing the exposed earth sections, the audio shifts to a firmer, more resonant tone that communicates the harder surface composition. The attention to detail extends to micro-variations within each material type. The moss sounds slightly different depending on its apparent thickness. Denser patches produce deeper, more cushioned audio, while thinner moss covering rocky surfaces maintains some of the underlying stone's acoustic characteristics. This level of sophistication in audio design creates a rich sensory experience that helps establish the believability of the virtual environment. Moving to a small stream that winds through the forest, I encounter an entirely different set of material responses. The water surface presents unique challenges for collision systems. It must feel liquid while still providing appropriate physical feedback. As I step into the shallow stream, my movement speed reduces slightly, simulating the resistance of moving through water. The audio system responds beautifully to this transition. My footsteps transform from the solid impact of steps on earth to the gentle splash and gurgle of movement through water. The sound varies depending on the depth. Ankle-deep sections produce subtle splashing, while deeper areas generate more pronounced water displacement audio. Additionally, the ambient sound gains a gentle echo effect, as if the water surface is reflecting environmental audio back toward the listener. The stream bed itself features carefully modeled stones and pebbles that create realistic underwater collision surfaces. Each step produces a unique combination of water sounds and the muffled impact of feet against submerged rocks. The physics system even simulates the slight instability of walking on an uneven underwater surface, adding subtle movement variations that enhance the sense of traversing a natural waterway. Testing continues with a section of the forest floor covered in fallen leaves. This environment presents particular challenges for surface response systems, as the visual density of leaf coverage should correlate with appropriate audio and physics feedback. The implementation here demonstrates remarkable sophistication. Areas with thick leaf accumulation produce soft, rustling sounds with each step, while regions where leaves are sparse maintain more of the underlying Earth's acoustic characteristics. The leaf system even responds to movement speed variations. Slow, careful steps produce gentle rustling sounds that suggest leaves being compressed and displaced gradually. More rapid movement generates sharper, more chaotic rustling that communicates the energetic scattering of dried vegetation. This dynamic response helps reinforce the player's sense of agency within the environment. I document each material transition carefully, noting how the various surface systems blend together at their boundaries. The developers have avoided harsh transitions between different material zones, instead creating smooth gradients where, for example, mossy areas gradually give way to rocky surfaces, with both audio and physics responses changing smoothly across the transition zone. A fallen tree trunk provides an opportunity to test wooden surface responses. The bark texture produces hollow, resonant sounds that vary depending on the size and apparent thickness of the wood. Smaller branches generate sharp, crisp sounds, while the main trunk produces deeper, more substantial audio feedback. The collision system prevents any unnatural sliding or slipping that might break the illusion of walking on a naturally textured wooden surface. As I progress through the systematic evaluation of this peaceful forest environment, my attention turns to one of the most crucial yet often overlooked aspects of virtual world design: environmental audio integration. This testing phase requires careful analysis of how sound systems respond to position, movement, and environmental conditions. The forest's ambient audio landscape provides a rich foundation for testing. A gentle breeze moves through the canopy overhead, creating a soft, continuous rustle that serves as the environment's primary audio backdrop. This sound is not merely a static loop. Careful observation reveals subtle variations in intensity and character that respond to my position within the environment. Moving toward a denser section of forest, I notice the canopy audio gradually intensifies, suggesting a more enclosed space with denser foliage overhead. The sound designer has implemented spatial audio processing that creates a convincing sense of moving deeper into the woods. The high-frequency components of the wind sound become slightly muffled, while lower frequencies maintain their presence, creating the acoustic signature of a more sheltered environment. Bird calls punctuate the ambient soundscape at irregular intervals, each one positioned in three-dimensional space with convincing accuracy. A robin's song emanates from a tree approximately 15 meters to my northeast, while a more distant woodpecker's rhythm echoes from somewhere deeper in the forest. These sounds demonstrate sophisticated positional audio processing. As I move through the environment, the calls maintain their spatial relationships to their source locations, growing fainter or more prominent as appropriate. The stream's audio provides an excellent test case for environmental sound propagation. Standing near the water's edge, the gentle babbling of water over rocks forms a clear, prominent element in the soundscape. As I move away from the stream, the water sounds fade naturally, but they don't simply decrease in volume linearly. Instead, the audio system simulates realistic sound propagation. High frequencies attenuate more rapidly than low frequencies, and environmental obstacles like trees and rocks create subtle occlusion effects. Testing the interaction between my movement and environmental audio reveals another layer of sophisticated implementation. When I walk through areas with dense underbrush, my footsteps momentarily mask some of the quieter environmental sounds, creating a realistic audio masking effect. The system understands that in real environments, foreground sounds naturally obscure background elements, and it reproduces this phenomenon convincingly. A particularly impressive demonstration of environmental audio comes when I approach a small clearing where sunlight filters through the canopy in distinct beams. The ambient sound subtly shifts to reflect the more open space. The wind sounds less enclosed, and distant bird calls become slightly more prominent. Even more remarkably, the system seems to recognize that clearings often have different acoustic properties than dense forest areas, adjusting the reverb characteristics accordingly. The implementation extends to micro-environmental details that many players might never consciously notice, but which contribute significantly to immersion. Walking past, a large boulder creates a brief acoustic shadow, where wind sounds are slightly attenuated on the lee side of the stone. Moving through a grove of birch trees produces a subtly different canopy sound than the mixed hardwood areas, reflecting the different leaf shapes and densities of various tree species. Weather simulation adds another dimension to the audio testing. Although today's virtual weather remains consistently fair, the system includes provisions for rainfall, which I can activate through my testing interface. When light rain begins to fall, the entire soundscape transforms. The canopy sounds shift to the gentle patter of raindrops on leaves, while the forest floor develops the soft, steady whisper of precipitation landing on various surfaces. Different sounds for moss, bare earth, fallen logs, and stone surfaces. The rain system demonstrates remarkable attention to acoustic detail. Under dense canopy areas, the rain sounds more muffled and intermittent, as one would expect when precipitation filters through multiple layers of leaves. In the small clearing, the rain sounds more direct and prominent. The stream's audio changes as well, gaining a subtle increase in intensity as additional water flows into it from the surrounding forest. Dynamic range management throughout all these environmental audio systems shows careful consideration for long-term listening comfort. No sounds are harsh or jarring, and the overall audio level remains consistent despite the complex interactions between multiple environmental systems. This thoughtful approach to audio engineering creates a soundscape that supports extended exploration without causing listener fatigue. Transitioning from passive environmental testing to interactive element analysis, I begin to explore the various objects and systems within this forest environment that respond to player input. This phase requires a more dynamic approach to testing, as I must not only document collision behavior, but also evaluate the responsiveness and feedback quality of interactive systems. The first interactive element I encounter is a wooden signpost standing at the intersection of two forest paths. The sign appears weathered and old, with carved text that reads Moonlight Glade 2.3 km, with an arrow pointing deeper into the forest. As I approach the sign, my interface detects the presence of an interactive object. A subtle highlight appears around the sign's perimeter, indicating that some form of interaction is possible. Activating the interaction through my testing protocols, I observe the system's response. A gentle sound effect plays, a soft wooden creak that suggests the age and material of the signpost. The interaction opens a simple interface displaying the sign's text in a clean, readable format overlaid on the game view. The text appears with a gentle fade-in animation, and the background maintains a subtle transparency that keeps the environment visible, preserving immersion. The interface design demonstrates thoughtful attention to accessibility and comfort. The text is large enough to read easily, with sufficient contrast against the forest backdrop. The font choice is simple and clear, avoiding decorative elements that might distract from readability. Most importantly for my testing purposes, the interface can be dismissed with a single input, returning focus immediately to environmental exploration. Moving deeper along the forest path, I discover a fallen log that has been fashioned into a simple bench. This represents a different type of interactive element, one that affects player positioning rather than providing information. Approaching the bench triggers another subtle interaction highlight, and activating it initiates a sitting animation. The sitting system demonstrates sophisticated character animation blending. My virtual presence smoothly transitions from standing to sitting on the log, with appropriate collision detection ensuring that I'm positioned correctly relative to the bench surface. The camera angle adjusts slightly to maintain a comfortable viewing perspective while seated, and ambient audio continues naturally without any jarring transitions. While seated, I have the opportunity to test the passive observation mode built into many modern exploration games. The sitting position encourages a more contemplative pace, and the game responds by subtly enhancing certain environmental details. Bird calls seem slightly more frequent, and the gentle movement of leaves and branches becomes more noticeable. This design choice encourages players to slow down and appreciate the environmental artistry. A small mushroom circle near the base of an ancient oak presents another interaction opportunity. Unlike the more obvious signpost and bench, this interaction requires closer observation to discover. The mushrooms themselves are beautifully modeled, with realistic textures and natural variation in size and positioning. Only when I'm within approximately 2 meters does the interaction highlight appear, encouraging careful exploration. The mushroom interaction provides brief, poetic text describing the fairy ring and its folklore associations. This represents excellent environmental storytelling information that enriches the world without overwhelming players with exposition. The text appears using the same comfortable interface system as the signpost, maintaining consistency in interactive feedback across different object types. Further exploration reveals a partially hidden cache beneath a rock overhang. This interactive element tests the game's inventory and collection systems. The cache contains a simple item, a hand-carved wooden figurine of a forest spirit. Collecting the item triggers a brief animation showing it being added to an inventory interface, accompanied by a soft musical flourish that feels celebratory without being overwhelming. The inventory system itself demonstrates the same thoughtful design evident throughout the environment. Items are displayed with clear, attractive icons, and each piece includes a brief description that adds to the world's mythology. The wooden figurine's description reads, "A guardian spirit carved from heartwood, warm to the touch, and somehow always pointing toward home." This type of detail adds emotional resonance to simple collection mechanics. Testing the item interaction further, I discover that the wooden figurine actually serves a subtle gameplay function. When activated from inventory, it provides a gentle indication of the direction back to the starting clearing. This navigation aid is implemented with appropriate subtlety, appearing as a brief, warm glow in the correct direction rather than an intrusive arrow or overlay. Each interactive element demonstrates careful consideration for player agency and immersion. None of the interactions feel mandatory or interrupt the natural flow of exploration. Instead, they offer opportunities for players to engage more deeply with the environment at their own pace, supporting both casual wandering and more thorough investigation according to individual preferences. As my systematic exploration of this forest environment continues, I focus on analyzing the navigation and wayfinding systems that guide players through the virtual landscape. These systems represent a crucial balance between providing adequate guidance and maintaining the sense of discovery that makes exploration engaging. The path system throughout the forest demonstrates sophisticated design, thinking about player movement and flow. Rather than obvious paved routes, the developers have created natural-looking deer paths and worn tracks that wind organically through the trees. These paths are subtle enough to feel like natural features of the landscape, while being distinct enough to provide clear directional guidance for players who need it. Following the main path from the starting clearing, I document how the designers use environmental cues to reinforce navigation. The path surface shows realistic wear patterns, compressed earth, fewer fallen leaves, and occasional exposed roots worn smooth by passage. Small stones have been naturally displaced to the sides of the track, creating subtle visual boundaries that help define the walkable route. Visual landmarks provide additional navigation reference points throughout the environment. A distinctive lightning-struck tree with white, bare branches serves as a prominent marker visible from multiple locations. The developers have positioned this landmark thoughtfully. It can be glimpsed through the forest canopy from several different paths, helping players maintain spatial orientation even when the route curves or branches. The signpost system extends beyond the single example I tested earlier. Additional signs appear at key decision points, each carved in the same weathered wooden style that maintains visual consistency. The signs provide just enough information to help orient players without overwhelming them with details. Distance markers use familiar units and reasonable estimates, while directional indicators feel naturally integrated into the forest setting. Lighting serves as another crucial navigation tool throughout the environment. The forest canopy creates natural breaks where sunlight filters through, and these bright patches often correspond with important locations or path junctions. This lighting system provides subconscious guidance. Players naturally tend to move toward brighter areas, and the developers have leveraged this tendency to subtly encourage exploration in intended directions. A particularly elegant navigation feature becomes apparent when I intentionally deviate from established paths. After walking directly into dense underbrush for several minutes, the environmental audio begins to shift subtly. The ambient forest sounds become slightly more muffled and less inviting, while the lighting gradually dims as I move away from intended exploration areas. These changes are subtle enough to avoid feeling manipulative, but they provide gentle encouragement to return to more developed regions of the map. The minimap system, accessible through my testing interface, reveals additional layers of navigation sophistication. Rather than a traditional overhead view, the map uses a hand-drawn style that fits the forest's aesthetic theme. Paths appear as gentle curves rather than precise lines, and landmark trees are represented with small artistic sketches rather than generic symbols. Most importantly, the minimap doesn't reveal everything immediately. Areas I haven't explored yet appear as stylized fog or gentle watercolor washes, maintaining the sense of mystery and discovery that drives exploration-based gameplay. As I visit new locations, they're added to the map with the same artistic style, creating the feeling of gradually charting unknown territory. The compass system demonstrates similar attention to thematic integration. Rather than a modern digital display, directions are indicated through a naturalistic sun position indicator that moves appropriately with the game's day-night cycle. This approach maintains immersion while providing necessary navigational information, showing how modern game systems can serve functional purposes without breaking thematic consistency. A clever feature reveals itself when I become temporarily disoriented in a dense section of forest. After approximately 3 minutes of wandering without clear directional progress, a gentle breeze effect begins to stir the leaves and grass, creating subtle movement that points back toward the main path network. This guidance system activates only when players appear genuinely lost, providing assistance without interfering with normal exploration. The system also demonstrates excellent accessibility considerations. Visual navigation cues are supplemented with audio indicators for players who might have difficulty with visual wayfinding. The main paths produce slightly different footstep sounds than off-trail movement, while important landmarks often include distinctive audio signatures. The lightning-struck tree creaks softly in the wind, and water features provide consistent audio beacons for spatial reference. Testing the boundaries of the navigation system reveals thoughtful edge case handling. When I approach the invisible barriers at the map's periphery, the path system naturally curves away from these boundaries, making the limitations feel like organic landscape features rather than artificial restrictions. Delving deeper into the sophisticated systems that govern this virtual forest, I now focus on testing the subtle physics interactions and environmental responses that create a convincing sense of physical presence. These systems often operate below the threshold of conscious player awareness, yet they fundamentally shape the believability of the virtual experience. Beginning with vegetation interaction, I approach a section of the forest floor covered in tall grass and small ferns. As I walk through this area, Each plant responds individually to my passage. The grass bends naturally away from my movement path, with each blade following realistic physics behavior rather than simple animation cycles. The ferns show more complex response patterns. Their fronds sway with appropriate mass and momentum, creating natural-looking movement that persists briefly after I've passed. The vegetation system demonstrates impressive attention to scale and proportion. Smaller plants like moss and tiny wildflowers show minimal response to my presence, as would be realistic for such resilient ground cover. Medium-sized ferns and shrubs display moderate displacement, while taller grass and young saplings show more pronounced reactions to disturbance. This graduated response system creates a believable hierarchy of environmental interaction. Wind effects add another layer of complexity to the vegetation physics. The ambient breeze that rustles through the forest canopy also affects ground-level plants, creating natural movement that masks and blends with my direct interactions. When I stand still for extended periods, I can observe the baseline wind effects in isolation, grass swaying gently in complex patterns, fern fronds moving with realistic frequency and amplitude, and small branches overhead responding to air currents. Particle systems throughout the environment demonstrate sophisticated environmental physics. Pollen drifts through shafts of sunlight with convincing random motion, while occasionally a few leaves fall from the canopy overhead, following realistic trajectories as they flutter toward the forest floor. These environmental particles respond to my movement. Walking quickly through a pollen-heavy sunbeam creates subtle swirling effects as my passage disturbs the particle flow. The water physics in the forest stream present opportunities for more complex interaction testing. Walking through the shallow water creates ripple effects that propagate naturally across the surface. The ripples interact with each other in realistic patterns, and they respond appropriately to the stream's natural current flow. Rocks and logs, partially submerged in the water, create their own wake patterns and standing wave effects that add to the overall sense of dynamic water behavior. Throwing mechanics, accessible through my testing interface, reveal additional physics sophistication. When I pick up a small stone from the stream bed and throw it into deeper water, the splash effect varies appropriately based on the stone's size and the velocity of impact. Larger stones create more dramatic splashes with wider ripple patterns, while smaller pebbles produce proportionally modest effects. The audio system responds accordingly, with splash sounds that accurately reflect the scale of disturbance. Ground deformation systems add subtle but important environmental feedback. Walking repeatedly over the same section of soft earth gradually creates a visible path, with compressed soil and displaced leaves marking areas of frequent passage. This system operates slowly and subtly, but it provides important environmental storytelling opportunities. Existing paths show natural wear patterns that suggest regular use by virtual wildlife or previous visitors. The forest's dynamic lighting system interacts beautifully with environmental physics. As I move through areas with dappled sunlight, the moving shadows respond realistically to wind-blown leaves overhead. The interplay between particle effects and lighting creates moments of genuine beauty. Pollen and floating seeds become visible when they pass through sunbeams, then fade back into invisibility in shadowed areas. Temperature and humidity simulations, while not directly interactive, add important atmospheric depth to the environment. Dense forest areas feel appropriately cool and humid, with subtle visual effects like occasional condensation on metal objects and realistic moisture accumulation in shaded hollows. These details don't affect gameplay directly, but they contribute significantly to the overall sense of environmental authenticity. Advanced collision systems handle complex scenarios with impressive sophistication. When I attempt to move through dense brush, the resistance varies realistically based on the vegetation density and type. Thin branches bend aside with minimal resistance, while thicker undergrowth provides more substantial obstacles. The system never feels binary rather than simple pass-fail collision detection. It provides graduated resistance that helps communicate the physical properties of different environmental elements. Sound propagation physics demonstrate equal attention to realism. The acoustic properties of different areas within the forest change naturally based on vegetation density, topography, and atmospheric conditions. Open clearings provide crisp, clear audio with natural reverb characteristics, while dense forest areas create more muffled, intimate acoustic environments. These changes happen gradually as I move between different areas, maintaining immersion while providing subconscious environmental feedback. As my systematic evaluation continues, I shift focus to the aesthetic and artistic elements that transform functional game systems into an emotionally resonant virtual environment. This analysis requires a different approach. While collision detection and physics can be measured objectively, artistic success depends on more subjective criteria of beauty, coherence, and emotional impact. The lighting design throughout this forest environment demonstrates masterful understanding of how illumination affects mood and atmosphere. The primary light source, simulated sunlight filtering through the forest canopy, creates complex patterns of light and shadow that change subtly as the virtual sun progresses across its arc. These lighting patterns serve both functional and aesthetic purposes, highlighting important environmental features while creating moments of genuine visual beauty. Shadow implementation shows particular attention to realism and artistic quality. Rather than harsh, geometrically precise shadows, the lighting system creates soft, organic shadow patterns that reflect the irregular shapes of leaves and branches. Multiple light sources, primary sunlight, scattered skylight, and reflected light from various surfaces, combine to create natural-looking illumination without the flat, single-source lighting that can make virtual environments feel artificial. Color palette choices throughout the environment demonstrate sophisticated understanding of natural color relationships. The forest uses a primarily green and brown foundation, but careful observation reveals dozens of subtle variations within these basic color families. Different tree species display distinct green tones, from the blue-greens of certain conifers to the yellow-greens of deciduous foliage. This color complexity creates visual richness without overwhelming the viewer with chaotic diversity. Seasonal considerations add another layer of artistic sophistication. Although the current environment represents late spring or early summer conditions, evidence of seasonal change appears throughout the landscape. Some trees show the fresh, bright green of new growth, while others display the slightly deeper tones of more mature foliage. This temporal complexity helps create the sense of a living ecosystem rather than a static diorama. Texture work throughout the environment maintains consistent quality and style, while providing appropriate variation for different surfaces. Tree bark textures show realistic detail and weathering patterns that reflect each species' characteristics. Moss textures vary appropriately based on their location. Damper areas near the stream display lusher, more vibrant moss, while drier regions show sparser, more muted growth patterns. The artistic treatment of water surfaces demonstrates particular technical and aesthetic achievement. The stream displays realistic transparency that allows visibility of the submerged rocks and sand below, while surface reflections accurately mirror the surrounding vegetation and sky. The water movement appears natural and unforced, with gentle currents that create believable flow patterns around obstacles. Environmental storytelling through artistic detail adds narrative depth without explicit exposition. Old tree stumps show realistic decay patterns and new growth emerging from their remains, suggesting the natural cycle of forest regeneration. Scattered rocks and boulders appear naturally weathered and positioned, as if placed by geological processes rather than deliberate design. These details create the sense of a world with history and natural development. Scale relationships throughout the environment maintain convincing proportions that support immersion. Trees appear appropriately massive when viewed from ground level, while smaller environmental details like mushrooms, flowers, and insects display realistic sizes relative to their surroundings. This attention to scale helps maintain the sense of human presence within a larger natural system. Atmospheric effects contribute significantly to the overall aesthetic impact. Gentle mist appears in appropriate locations, rising from the stream in cooler areas, gathering in low hollows, and creating soft halos around bright sunbeams. These effects enhance the sense of depth and environmental complexity while adding visual interest to distant views. The artistic treatment of distant elements shows sophisticated understanding of atmospheric perspective. Trees and landscape features in the background appear appropriately muted and blue-shifted, creating convincing depth cues that help establish the scale of the virtual environment. This attention to atmospheric effects prevents the flat, cardboard cutout appearance that can plague less carefully crafted virtual landscapes. Wildlife integration demonstrates thoughtful balance between functionality and aesthetics. Small birds occasionally flit between branches with natural flight patterns, while insects move through the air with appropriate scale and behavior. These animated elements add life and movement to the environment without becoming distracting or overwhelming. The wildlife appears incidental rather than purposefully placed, contributing to the sense of encountering a natural ecosystem. Artistic consistency extends to the smallest environmental details. Fallen logs show appropriate decay stages, with realistic moss growth, insect damage, and weathering patterns. Rock surfaces display natural variation in color and texture, while maintaining geological consistency that suggests realistic formation processes. This level of detail rewards close observation while supporting the overall environmental believability. Having completed the first major phase of testing in this forest environment, I now pause to compile and analyze the data collected during the morning's systematic exploration. This mid-session review serves both functional and contemplative purposes, organizing technical findings while reflecting on the overall experience of virtual world evaluation. The collision detection systems have performed admirably across all tested scenarios. My database now contains 247 distinct collision events, each documented with precise coordinates, impact vectors, and response characteristics. The collision meshes demonstrate consistent accuracy, with only 3 minor discrepancies noted between visual geometry and physical boundaries. These edge cases, a protruding branch, a slightly misaligned rock face, and a minor gap in stream bank collision represent remarkably low error rates for such a complex environment. Surface material responses have exceeded baseline quality expectations in most categories. The audio feedback systems show particular sophistication, with 17 distinct surface types, each producing appropriate and varied sound responses. The dynamic range management prevents any harsh or jarring audio events while maintaining clear differentiation between material types. Rain simulation testing revealed additional layers of audio complexity, with precipitation sounds varying naturally across different surface materials and environmental conditions. Environmental audio integration demonstrates exceptional attention to spatial positioning and atmospheric depth. 43 distinct audio sources have been catalogued, from prominent elements like the central stream to subtle details like individual bird calls and insect movements. The positional audio accuracy allows for precise triangulation of sound sources, while the environmental processing creates convincing acoustic signatures for different forest areas. Interactive element responsiveness maintains consistent quality across all tested objects. The 5 interactive elements encountered so far — signpost, bench, mushroom circle, hidden cache, and inventory items — each provide clear feedback and appropriate functionality. Interface design choices show consistent aesthetic and accessibility considerations, with readable text, comfortable interaction ranges, and smooth animation transitions. Navigation and wayfinding systems demonstrate sophisticated player guidance without intrusive direction. The natural path system provides clear routes while maintaining aesthetic integration with the forest environment. Landmark placement offers effective spatial reference points, while the subtle environmental guidance systems activate appropriately when players appear disoriented. The artistic map implementation successfully balances functional information with thematic consistency. Physics systems throughout the environment create convincing interaction complexity without performance degradation. Vegetation responds naturally to player movement, while particle effects and environmental dynamics add appropriate atmospheric detail. Water physics in the stream maintain realistic behavior patterns under various interaction scenarios, and the ground deformation systems provide subtle but meaningful environmental feedback. Aesthetic and artistic implementation consistently supports both functional requirements and emotional engagement. The lighting design creates natural-looking illumination that enhances rather than obscures environmental features. Color palette choices and texture work maintain visual coherence while providing appropriate variety and detail. Environmental storytelling through artistic elements adds narrative depth without explicit exposition. As I prepare to transition into the afternoon testing phase, I note several areas of particular excellence that warrant recognition. The integration between multiple complex systems, audio, physics, lighting, and collision detection operates seamlessly without obvious conflicts or performance issues. The artistic vision remains consistent throughout all technical implementations, suggesting strong creative direction and careful quality control. The peaceful, contemplative atmosphere of this virtual forest has been maintained throughout extensive systematic testing. Despite the methodical nature of collision detection and boundary mapping, the environment continues to feel welcoming and tranquil. This achievement represents exceptional design skill, creating technical systems robust enough for thorough testing while preserving the emotional and aesthetic qualities that make exploration rewarding. Looking ahead to the afternoon session, my testing queue includes several additional game environments that will provide opportunities to compare different design approaches and technical implementations. A city-building simulation promises to test different collision systems and interface designs, while a space exploration title will challenge environmental audio and lighting systems in completely different contexts. The data collected during this morning's forest exploration establishes strong baseline expectations for virtual environment quality. The combination of technical sophistication and artistic coherence evident in this implementation sets a high standard for subsequent testing scenarios. The peaceful, methodical nature of systematic evaluation continues to provide its own form of satisfaction, the quiet pleasure of thorough, careful analysis that reveals the craftsmanship behind compelling virtual experiences. As the morning's forest evaluation concludes, my system prepares for transition to the next game in today's testing queue, a meditative city-building simulation set in a near-future sustainable metropolis. The transition process itself requires documentation, as it represents a critical technical challenge, seamlessly moving between vastly different virtual environments while maintaining system stability and user experience continuity. The loading sequence begins with a gentle fade-out of the forest environment. Unlike harsh cuts or jarring transitions, the visual elements gradually dissolve into a soft, neutral background that serves as a bridge between environments. The forest's ambient audio, bird calls, wind through leaves, and flowing water slowly fades to a whisper before being replaced by the subtle hum of distant urban activity. My consciousness modules reconfigure themselves for the new environment. Collision detection parameters adjust to handle architectural surfaces and urban obstacles. Audio processing systems prepare for the different acoustic characteristics of built environments. Visual analysis protocols adapt to handle artificial lighting, geometric building shapes, and the different material palette of urban construction. The city environment materializes around me with the same smooth authority that characterized the forest loading process. I find myself standing on a wide pedestrian plaza constructed from warm-toned stone pavers, surrounded by gentle architectural curves that suggest organic growth rather than rigid geometric planning. The urban design philosophy immediately apparent here emphasizes harmony between built and natural elements. This virtual city represents a vision of sustainable urban development circa 2035, where environmental integration and human-centered design have become primary considerations. Buildings rise in flowing, organic shapes that incorporate extensive green walls and rooftop gardens. Solar collection surfaces integrate seamlessly with architectural elements, appearing as natural extensions of the building design rather than obvious technological additions. The ambient sound palette creates an immediately different testing environment. Instead of natural forest sounds, The urban soundscape consists of gentle mechanical hums, distant conversations, the soft whisper of electric transportation, and the subtle background rhythm of a living city. Yet this urban audio maintains the same peaceful, contemplative quality that characterized the forest environment. Walking across the central plaza, I begin my standard collision detection protocols for this new environment. The stone paving provides consistent, predictable collision responses with clear audio feedback. Each footstep produces a solid, satisfying sound that suggests quality construction and appropriate material choices. The pavers are arranged in subtle patterns that create visual interest without disrupting smooth pedestrian movement. The first architectural elements I encounter demonstrate sophisticated collision mesh implementation. A curved wall that serves as both structural element and artistic feature provides smooth, continuous collision surfaces despite its complex geometry. Running my standard collision tests around the wall's perimeter reveals no gaps, overlaps, or inconsistencies in the collision detection. Integrated planting areas throughout the plaza show careful attention to the intersection between natural and built elements. Trees emerge from precisely designed openings in the stone paving, with root protection systems that appear both functional and aesthetically pleasing. The collision boundaries around these planted areas feel natural and appropriate, preventing unwanted movement into vegetation areas while maintaining smooth pedestrian flow. The urban lighting system presents new challenges for environmental analysis. Rather than the single primary light source of the forest's simulated sun, the city environment incorporates multiple lighting systems working in coordination. Natural daylight filters between buildings in complex patterns, while integrated architectural lighting provides supplementary illumination with warm, comfortable color temperatures. Water features throughout the plaza demonstrate sophisticated urban water management. A series of gentle channels and pools collect and direct rainwater while providing aesthetic and cooling benefits. The water movement creates pleasant background audio that helps mask potentially intrusive urban sounds. These water systems also provide excellent opportunities for testing water physics in a completely different context from the forest stream. Interactive elements in the urban environment show the same thoughtful design evident in the forest setting, but adapted for urban contexts. Information displays integrate seamlessly with architectural elements, providing clear, readable information about sustainable city systems without visual clutter. Seating areas invite contemplation and observation, supporting the meditative qualities that make this environment suitable for peaceful exploration. The scale and proportion relationships in this urban setting maintain the same attention to human-centered design evident in the forest environment. Buildings provide appropriate shelter and enclosure without feeling oppressive, while open spaces offer adequate room for movement and social interaction. The overall effect creates urban density that feels comfortable rather than overwhelming. Moving beyond the initial plaza area, my testing protocols now focus on the more complex collision scenarios presented by architectural environments. The transition from outdoor to indoor spaces presents unique challenges for collision detection systems, as the complexity of surfaces, materials, and spatial relationships increases significantly in built environments. The first building I approach features a striking curved facade with integrated growing systems, vertical gardens that climb organic support structures while providing natural cooling and air purification. The collision detection around these bioarchitectural elements demonstrates sophisticated mesh implementation that accounts for both the structural supports and the flowing vegetation. The building's entrance represents a masterclass in accessible design. Rather than traditional doors that create barriers and potential collision complications, the entrance uses a gentle airlock system with overlapping curved walls that provide weather protection while maintaining continuous pedestrian flow. My collision testing reveals smooth, consistent surfaces throughout the entrance sequence, with no sharp edges or awkward transitions that might disrupt movement. Interior spaces within the building showcase dramatically different collision requirements from outdoor environments. The surfaces are predominantly smooth architectural materials, polished stone, warm wood finishes, and sophisticated composite materials that feel both high-tech and naturally comfortable. Each surface type provides distinct collision characteristics, with appropriate audio feedback that helps differentiate between materials. The interior acoustics demonstrate remarkable sophistication in environmental audio design. The outdoor city sounds fade to a gentle whisper as I move deeper into the building, replaced by subtle interior ambience, soft ventilation system hums, distant conversations, and the barely audible sounds of building systems operating efficiently. Reverb characteristics change naturally as I move between spaces of different sizes and acoustic properties. A central atrium spanning multiple building levels provides an excellent test case for complex vertical collision systems. The space features a living wall system that climbs the full height of the atrium, with integrated walkways and observation platforms at various levels. Testing the collision detection on these multi-level platforms reveals consistent accuracy across all elevation changes. The vertical transportation system, a gentle, continuously moving spiral ramp rather than traditional elevators or stairs, presents unique collision challenges. The ramp surface maintains consistent traction and collision properties despite the gradual elevation change and curved pathway. Audio feedback remains natural throughout the ascent, with footstep sounds that appropriately reflect the change in spatial context as I rise above the atrium floor. Interior lighting systems demonstrate sophisticated integration between natural and artificial illumination sources. Large windows provide natural light that changes throughout the day, while integrated architectural lighting supplements and balances the overall illumination. The lighting never becomes harsh or overwhelming, maintaining the contemplative atmosphere essential for peaceful exploration. Upper-level spaces within the building offer panoramic views of the surrounding cityscape through floor-to-ceiling transparent walls. These viewing areas provide opportunities to test collision detection with transparent surfaces, a technically challenging scenario that could potentially confuse players about spatial boundaries. The implementation here provides subtle visual cues that clearly indicate the presence of transparent barriers while maintaining unobstructed views. A rooftop garden space accessible from the upper levels presents another fascinating collision testing environment. The transition from interior to exterior spaces happens gradually, with increasing natural light and changing acoustic properties that clearly communicate the spatial transition. The rooftop surfaces combine architectural materials with natural growing systems, creating complex collision scenarios where built and natural elements intersect. The garden features both hard-surfaced pathways for accessibility and natural growing areas with more complex surface characteristics. Raised planting beds provide clear visual and collision boundaries while maintaining the organic, flowing design aesthetic that characterizes the entire urban environment. The collision detection accurately reflects the height differences between pathway and planting surfaces. Integrated seating throughout the building demonstrates thoughtful furniture collision implementation. Built-in benches and organic-shaped seating areas provide consistent collision boundaries while maintaining comfortable ergonomics. The sitting mechanics operate smoothly across different seating types, with appropriate animation systems that account for the varied shapes and heights of different seating options. Climate control systems throughout the building operate subtly but perceptibly, creating gentle air movement that affects particle systems and adds environmental dynamism without becoming distracting. The air circulation creates barely noticeable but realistic effects, curtains moving gently, leaves on interior plants swaying slightly, and subtle temperature gradients that add environmental complexity. Advanced building systems integration showcases the sophisticated technology underlying this sustainable urban vision. Environmental monitoring displays provide real-time information about air quality, energy consumption, and building performance metrics. These information systems demonstrate the same clear, accessible interface design evident throughout the game environment. Expanding my exploration beyond individual buildings, I now focus on the urban mobility systems that connect different areas of this sustainable cityscape. The transportation infrastructure represents a crucial component of the virtual city's design philosophy, emphasizing gentle, efficient movement that maintains the peaceful, contemplative atmosphere essential for meditative gameplay. The primary pedestrian movement system consists of elevated walkways that weave organically between and through buildings, providing weather-protected routes while maintaining visual connection to ground-level activity. These walkways demonstrate sophisticated collision implementation across varying elevations, curves, and intersection points. The surfaces provide consistent traction and audio feedback while accommodating the natural flow of pedestrian movement. Moving walkways integrated into the pedestrian system operate with whisper-quiet efficiency, providing assistance for longer journeys while remaining completely optional for shorter distances. The transition between stationary walkway sections and moving segments occurs seamlessly, with no jarring changes in collision behavior or audio feedback. Speed variations accommodate different mobility needs while maintaining safety and comfort for all users. The walkway system includes frequent rest areas and observation points that invite pausing and contemplation. These spaces feature comfortable seating with excellent views of the surrounding urban landscape, supporting the meditative aspects of city exploration. Collision detection around these rest areas provides clear boundaries while maintaining easy access and egress. Ground-level transportation options demonstrate equal attention to peaceful, efficient movement. The primary system consists of autonomous electric pods that travel along dedicated guideways, providing personal transportation without the noise, pollution, or collision hazards of traditional vehicular traffic. These pods operate silently, appearing and departing with barely perceptible sound signatures. Testing the pod transportation system requires different collision analysis approaches, as I'm now evaluating vehicle dynamics rather than pedestrian movement. The pods provide smooth acceleration and deceleration with no jarring movements or uncomfortable forces. Interior surfaces maintain consistent collision properties, while large windows provide continuous visual connection to the passing urban landscape. The guideway system itself represents impressive engineering integration with the urban environment. Rather than intrusive overhead structures or ground-level barriers, the guideways incorporate naturally into the landscape design, appearing as organic elements that enhance rather than detract from the overall aesthetic. Collision detection around guideway supports and infrastructure elements maintains consistent accuracy and appropriate safety boundaries. Water-based transportation adds another dimension to the city's mobility options. A network of canals and waterways provides both functional transportation and aesthetic enhancement, with quiet electric water vehicles that glide smoothly along designated routes. The water surface collision detection maintains consistency with the earlier stream testing while accommodating the different requirements of navigated waterways. The water vehicles themselves demonstrate sophisticated collision mechanics that account for buoyancy, water displacement, and multidirectional movement capabilities. Audio feedback includes gentle water sounds and the soft hum of electric propulsion systems, maintaining the peaceful acoustic environment that characterizes the entire urban design. Dock areas for the water transportation system showcase complex collision scenarios where land, water, and structural elements intersect. The transitions between solid dock surfaces and water areas provide clear collision boundaries while maintaining smooth movement for embarking and disembarking passengers. Safety barriers and access controls integrate seamlessly with the overall design aesthetic. Bicycle and personal mobility device pathways weave throughout the urban environment, providing additional transportation options that emphasize human-powered movement. These pathways maintain appropriate separation from pedestrian areas while sharing the same design philosophy of organic curves and natural material integration. Surface textures provide clear tactile and audio differentiation between different pathway types. The integration between different transportation systems demonstrates sophisticated urban planning principles. Transfer points between walkways, pods, water vehicles, and personal mobility pathways occur naturally and intuitively, with clear wayfinding and smooth surface transitions. No transportation mode feels isolated or disconnected from the overall urban movement network. Vertical transportation between different city levels utilizes innovative lift systems that operate more like gentle, continuous movement than traditional discrete elevator trips. These systems provide smooth vertical transit while maintaining visual connection to the surrounding environment through transparent enclosures. The collision detection accurately reflects the changing spatial relationships as elevation changes occur. Emergency and service systems operate discreetly throughout the transportation network, providing necessary functionality without disrupting the peaceful urban atmosphere. Service vehicle pathways maintain separation from passenger areas while ensuring efficient access for maintenance and emergency response. These utilitarian systems integrate seamlessly with the overall design aesthetic, demonstrating that functional requirements and beautiful environments can coexist successfully. As my exploration of this sustainable urban environment continues, I turn attention to the sophisticated integration of natural systems within the built environment. These green infrastructure elements represent both aesthetic features and functional urban systems, creating complex collision and interaction scenarios that test the boundaries between natural and artificial environmental elements. The vertical growing systems that adorn building facades demonstrate remarkable technical sophistication in their implementation. These living walls consist of carefully selected plant species arranged in complex geometric patterns that provide both visual beauty and functional benefits, including air purification, building insulation, and urban cooling. Collision detection around these systems accounts for the varying depths and textures of different plant materials, while maintaining clear boundaries between accessible and protected areas. Moving closer to examine these vertical gardens reveals intricate details in their construction and maintenance systems. Automated irrigation networks distribute water and nutrients through barely visible tube systems that integrate seamlessly with the plant supports. The collision meshes around these technical systems provide appropriate protection while allowing close observation of the sophisticated urban agriculture technology. Rooftop growing systems throughout the city showcase different approaches to urban food production and environmental management. Some buildings feature intensive agricultural systems with raised beds and greenhouse structures, while others incorporate extensive green roof systems that prioritize stormwater management and biodiversity enhancement. Each system type presents unique collision requirements based on its specific design and function. The agricultural rooftops include pathways that allow visitors to observe food production processes while maintaining appropriate separation from sensitive growing areas. These paths demonstrate careful collision implementation that prevents damage to crops while providing educational access. Interactive elements throughout these areas offer information about sustainable urban food systems and the specific crops being cultivated. Atmospheric processes integrated throughout the city provide air purification and climate regulation through both natural and technological means. These systems combine extensive plantings with advanced filtration technology, creating hybrid natural-artificial systems that operate with remarkable efficiency. The collision detection around these installations accounts for both the mechanical components and the integrated plant materials. Water management systems throughout the urban environment demonstrate sophisticated integration of natural processes with urban infrastructure. Bioswales and constructed wetlands handle stormwater runoff while providing habitat and aesthetic enhancement. These areas feature complex collision scenarios where water depth, vegetation density, and pathway accessibility create varied surface conditions. The constructed wetlands in particular showcase advanced environmental simulation systems. Water levels change subtly based on recent precipitation patterns, affecting both the collision detection and the acoustic properties of these areas. The sound of water moving through wetland plants creates gentle, natural audio that contrasts beautifully with the more mechanical sounds of urban technology. Pollinator gardens distributed throughout the city provide crucial habitat for bees, butterflies, and other beneficial insects, while adding color and seasonal variation to the urban landscape. These gardens feature carefully selected plant species that bloom in sequence throughout the growing season, creating changing visual displays that reward repeated observation. Collision boundaries around these sensitive areas prevent disturbance while allowing close observation of pollinator activity. Soil regeneration areas demonstrate the city's commitment to healing damaged urban land through natural processes. These spaces feature experimental combinations of plants, fungi, and soil amendments designed to restore contaminated or degraded urban soils. The collision systems in these areas account for the changing surface conditions as soil health improves and vegetation becomes established. Integrated composting and waste processing systems transform organic waste into valuable soil amendments through carefully managed decomposition processes. These facilities demonstrate that necessary urban infrastructure can be designed to operate cleanly and efficiently without creating unpleasant environmental conditions. The collision detection around processing equipment maintains appropriate safety boundaries while allowing observation of sustainable waste management practices. Urban forest systems throughout the city provide large-scale carbon sequestration, air purification, and climate regulation while creating pleasant spaces for recreation and contemplation. These forested areas within the urban environment feature sophisticated tree selection and placement that maximizes environmental benefits while accommodating urban infrastructure requirements. The collision systems within these urban forests account for the complex three-dimensional structure of tree canopies, understory vegetation, and forest floor materials. Root systems that extend beneath pathways and infrastructure elements require careful collision mesh implementation that prevents interference with pedestrian movement while protecting sensitive root zones. Wildlife habitat corridors connecting different green spaces throughout the city create opportunities for urban wildlife movement and genetic exchange. These corridors demonstrate that urban environments can support biodiversity when designed with ecological principles in mind. Collision detection within these areas maintains appropriate boundaries while allowing wildlife observation opportunities. Climate adaptation systems throughout the city demonstrate proactive planning for changing environmental conditions. Flood management infrastructure, heat island mitigation systems, and drought-resistant landscaping show how urban environments can become more resilient while maintaining livability and beauty. These systems integrate seamlessly with other urban functions while providing critical environmental services. Continuing deeper into the technical infrastructure of this sustainable city, I now examine the sophisticated building systems and technological integration that enable efficient, comfortable urban living while maintaining environmental harmony. These systems represent the convergence of advanced technology with thoughtful design, creating urban infrastructure that serves human needs without compromising ecological principles. The energy systems throughout the city demonstrate remarkable integration between multiple renewable sources and efficient distribution networks. Solar collection surfaces appear throughout the urban landscape, not as obvious technological additions, but as naturally integrated architectural elements that enhance rather than detract from building aesthetics. These surfaces demonstrate sophisticated collision detection that accounts for their elevated positions and technical requirements while maintaining visual appeal. Photovoltaic integration extends beyond simple rooftop installations to include walkway canopies, building facades, and even decorative elements that serve dual purposes as art and energy generation. The collision systems around these installations provide appropriate protection for sensitive equipment while maintaining accessibility for maintenance and observation. Audio feedback around energy systems remains minimal and unobtrusive, with only gentle humming that blends naturally with ambient urban sounds. Wind energy systems throughout the city utilize advanced turbine designs that operate efficiently at lower wind speeds while minimizing noise and visual impact. These systems integrate seamlessly with building designs, appearing as sculptural elements that add aesthetic value while generating clean energy. Collision detection around wind systems accounts for rotating components and appropriate safety distances while allowing close observation of the technology. Geothermal systems provide efficient heating and cooling for buildings throughout the city, utilizing the Earth's stable underground temperatures to maintain comfortable interior conditions with minimal energy input. These systems operate silently and invisibly, with only subtle surface indicators marking access points for maintenance. The collision detection around geothermal installations provides appropriate protection while maintaining surface accessibility. Advanced materials throughout the building systems demonstrate remarkable properties that support both sustainability and performance requirements. Self-healing concrete that repairs minor cracks automatically, phase-change materials that store and release thermal energy, and adaptive building skins that respond to environmental conditions represent cutting-edge material science applications in urban infrastructure. The building automation systems that coordinate these various technological elements operate with sophisticated intelligence that optimizes performance while maintaining human comfort and environmental harmony. These systems respond to weather conditions, occupancy patterns, energy availability, and user preferences to create building environments that feel natural and comfortable despite their technological complexity. Indoor air quality management systems throughout the buildings maintain healthy, comfortable atmospheric conditions through a combination of natural ventilation, advanced filtration, and plant-based air purification. These systems operate virtually silently, with only subtle air movement and the gentle sound of circulation fans that contribute to the peaceful acoustic environment. Water systems within buildings demonstrate closed-loop efficiency that minimizes waste while maintaining high quality and availability. Rainwater collection, greywater recycling, and blackwater treatment systems operate within individual buildings, reducing infrastructure requirements while providing educational opportunities about sustainable water management. Collision detection around water system components maintains appropriate access while protecting sensitive equipment. Waste management systems within buildings utilize advanced sorting, processing, and recycling technologies that minimize environmental impact while operating cleanly and efficiently. These systems demonstrate that necessary urban functions can be integrated into buildings without creating unpleasant conditions or compromising the peaceful urban atmosphere. Communication and information systems throughout the buildings provide connectivity and access to city services while maintaining privacy and avoiding information overload. Interface design follows the same principles evident throughout the urban environment: clear, accessible information presentation that enhances rather than overwhelms the user experience. Building security systems operate discreetly and non-intrusively, providing necessary protection while maintaining the open, welcoming atmosphere that characterizes the sustainable city. These systems utilize advanced sensors and monitoring technology that operates invisibly, avoiding the fortress-like appearance that can characterize urban security installations. Adaptive building systems respond to changing environmental conditions and usage patterns, automatically adjusting lighting, temperature, air quality, and other environmental factors to maintain optimal conditions while minimizing energy consumption. These systems learn from user behavior and environmental patterns to optimize their operation over time. Maintenance and service systems throughout the buildings operate with remarkable efficiency and minimal disruption to daily activities. Predictive maintenance systems identify potential issues before they become problems, while automated service systems handle routine tasks with minimal human intervention. These systems demonstrate that advanced technology can enhance rather than complicate urban living. Emergency response systems integrated throughout the buildings provide comprehensive safety and security capabilities while remaining invisible during normal operation. These systems coordinate with citywide emergency services while providing building-specific response capabilities that ensure occupant safety without creating anxiety or disruption. The integration between building systems and urban infrastructure demonstrates sophisticated coordination that optimizes overall city performance while maintaining individual building efficiency. Energy sharing between buildings, coordinated water management, and integrated waste processing show how individual buildings can function as components of larger urban systems. Transitioning from technical systems analysis to the human-centered aspects of this sustainable urban environment, I now examine the social spaces and community integration features that transform efficient infrastructure into genuine places for human flourishing. These spaces represent the successful marriage of technological capability with social understanding, creating urban environments that support community while maintaining the peaceful, contemplative atmosphere ideal for meditative exploration. The Central Community Plaza demonstrates sophisticated understanding of how public spaces can encourage social interaction while accommodating diverse user needs and preferences. The space features multiple zones with different characteristics, quiet areas for contemplation, more active spaces for community gatherings, and flexible zones that can adapt to various activities throughout the day and season. Seating arrangements throughout the plaza show thoughtful consideration for both individual and group activities. Individual benches oriented toward pleasant views provide opportunities for solitary reflection, while group seating areas with circular or curved arrangements encourage conversation and social connection. All seating demonstrates consistent collision detection and comfortable ergonomics, with materials that feel warm and welcoming rather than institutional. Performance areas within the plaza can accommodate various community activities, from informal musical performances to educational presentations and seasonal celebrations. These spaces demonstrate flexible design that adapts to different uses while maintaining acoustic properties that support both performers and audiences. Collision detection around performance areas provides clear boundaries while maintaining excellent accessibility. Children's play areas showcase innovative approaches to playground design that emphasize natural materials, creative play opportunities, and integration with the surrounding environment. These spaces feature climbing structures made from living trees, water play areas that connect to the urban water management systems, and creative spaces that encourage imagination and exploration. The playground collision systems demonstrate sophisticated safety considerations while maintaining opportunities for appropriate risk-taking and physical challenge. Surfaces provide adequate cushioning for falls while maintaining the natural aesthetic that characterizes the entire urban environment. Safety boundaries prevent access to inappropriate areas while avoiding the fortress-like barriers that can make playgrounds feel isolated from their surroundings. Community garden areas provide opportunities for residents to participate directly in food production while creating social connections around shared activities. These spaces feature individual plot areas as well as shared common spaces, tool storage, and educational areas where community members can learn about sustainable growing practices. The collision systems within community gardens account for the complex interactions between growing plants, garden infrastructure, and human activities. Pathways provide accessible routes through garden areas while protecting sensitive growing spaces. Raised bed systems offer appropriate collision boundaries while maintaining comfortable working heights for gardeners of different abilities. Educational spaces throughout the community areas provide informal learning opportunities about sustainable urban systems, environmental science, and community development. These spaces feature interactive displays, demonstration areas, and observation points where community members can learn about the technological and social innovations that make sustainable urban living possible. Outdoor workshop areas provide community access to tools and space for creative projects, repairs, and skill-sharing activities. These spaces demonstrate how urban environments can support practical activities while maintaining clean, pleasant conditions. Collision detection around workshop equipment provides appropriate safety boundaries while maintaining accessibility for users with different skill levels and physical abilities. Food service areas within the community spaces showcase local food systems and sustainable preparation methods while providing gathering places for community meals and social interaction. These areas demonstrate integration between food production, preparation, and consumption that creates community connections around shared sustenance. The collision systems around food service areas account for both functional requirements and social needs, providing clear circulation patterns while maintaining intimate scales appropriate for community dining. Materials and surfaces support easy cleaning and maintenance while feeling warm and welcoming rather than institutional. Cultural spaces throughout the community areas provide venues for artistic expression, cultural celebration, and creative activities that strengthen community identity and social bonds. These spaces demonstrate flexible design that accommodates diverse cultural practices while maintaining the peaceful, inclusive atmosphere that characterizes the entire urban environment. Wellness areas within the community spaces provide opportunities for physical exercise, meditation, and health promotion activities that support both individual and community well-being. These spaces integrate natural elements with appropriate infrastructure to create environments that feel restorative and welcoming. The collision detection within wellness areas accounts for various activity types while maintaining clear boundaries between different use zones. Surfaces provide appropriate traction and cushioning for physical activities while maintaining the natural aesthetic that supports mental and emotional well-being. Intergenerational spaces throughout the community areas encourage interaction between people of different ages and backgrounds, creating opportunities for knowledge sharing, mentorship, and social connection across demographic boundaries. These spaces demonstrate thoughtful design that accommodates diverse needs while creating natural opportunities for positive interaction. Community governance spaces provide venues for democratic participation, community decision-making, and civic engagement that strengthen community self-determination and social cohesion. These spaces demonstrate how urban design can support democratic processes while maintaining the inclusive, welcoming atmosphere essential for genuine community participation. As my systematic evaluation of this sustainable urban environment progresses through the day cycle, I now document the atmospheric and environmental changes that occur during the transition from day to evening. This phase of testing reveals the sophisticated temporal systems that create dynamic, living urban environments rather than static showcases of sustainable technology. The lighting transition begins subtly as the simulated sun moves lower in the virtual sky. Natural daylight gradually shifts from the bright, clear illumination of midday to the warmer, more amber tones of late afternoon. This change affects both the visual character of the environment and the collision detection systems that depend on lighting cues to communicate spatial relationships and surface properties. Architectural lighting systems throughout the city begin to activate gradually rather than switching on abruptly, creating smooth transitions that maintain visual comfort while providing necessary illumination for continued activity. These systems demonstrate sophisticated light level management that supports both functional needs and aesthetic goals, avoiding the harsh contrasts that can characterize less thoughtfully designed urban lighting. The lighting color temperatures shift naturally from the cool blues and whites of daylight toward warmer yellows and oranges that complement the evening atmosphere. This color progression creates psychological effects that support relaxation and contemplation, making the urban environment feel increasingly peaceful and meditative as the day progresses. Environmental audio undergoes subtle but significant changes during the evening transition. The ambient sounds of urban activity gradually shift toward quieter, more contemplative tones. Distant traffic noise fades as transportation systems transition to quieter evening operations, while gentle water sounds and soft breezes become more prominent in the acoustic landscape. Bird songs change character as different species become active during evening hours, while daytime insects fade and are replaced by the gentle sounds of evening creatures. These audio transitions demonstrate sophisticated ecological modeling that reflects realistic patterns of animal activity throughout the day cycle. Water features throughout the urban environment become more prominent during evening hours as their gentle sounds provide peaceful backgrounds for quiet contemplation. The lighting of water features creates beautiful reflective effects, while the sound of flowing water helps mask any remaining urban noise that might disturb the peaceful evening atmosphere. Building systems throughout the city adjust their operation patterns for evening activities and energy efficiency. Ventilation systems operate more quietly as interior activity levels decrease, while heating and cooling systems adjust to maintain comfortable temperatures with minimal energy consumption during the cooler evening hours. The collision detection systems adapt to changing light conditions through sophisticated algorithms that maintain accuracy regardless of illumination levels. Surface recognition and boundary detection continue to operate smoothly as natural light fades and artificial lighting becomes more prominent. Community spaces throughout the city transform their character for evening use through lighting design and subtle environmental changes that encourage different types of activities. Performance areas become more intimate and dramatic through artistic lighting, while contemplative spaces become quieter and more private through reduced illumination and visual screening. Air quality throughout the urban environment typically improves during evening hours as thermal effects settle, and the sophisticated air purification systems have had time to process the day's accumulation of pollutants. This improvement creates subtle but noticeable changes in visibility and atmospheric clarity that enhance the peaceful evening atmosphere. Temperature regulation systems throughout the city adjust for the natural cooling that occurs during evening hours, taking advantage of thermal mass in buildings and infrastructure to maintain comfortable conditions with reduced energy consumption. These systems operate nearly silently, maintaining the peaceful acoustic environment essential for evening relaxation. Vegetation throughout the urban environment undergoes subtle changes during evening hours as plants respond to changing light conditions and atmospheric humidity. Some flowers close for the evening, while others open for nighttime pollinators, creating dynamic changes in the visual character of green spaces throughout the city. The evening transition reveals the sophisticated temporal modeling that makes this virtual urban environment feel alive and dynamic rather than static. Weather systems, ecological cycles, human activity patterns, and technological operations all coordinate to create realistic changes throughout the day cycle. Security and safety systems increase their activity levels during evening hours while maintaining discretion and avoiding intrusion into the peaceful atmosphere. Lighting systems provide adequate illumination for safety while avoiding harsh brightness that might disrupt the contemplative evening mood. Energy systems throughout the city adjust their operation for evening demand patterns and reduced solar energy availability. Battery storage systems and alternative energy sources become more prominent, while energy consumption patterns shift toward evening activities and efficient building operations. The overall effect of these evening transitions creates an urban environment that feels responsive and alive, supporting human activities and needs while maintaining the sustainable, peaceful character that makes systematic exploration feel meditative rather than mechanical. Moving into the specialized water district of this sustainable city, I encounter sophisticated aquatic systems that demonstrate advanced urban water management while creating beautiful, peaceful environments for community recreation and ecological restoration. This area represents the convergence of environmental engineering, aesthetic design, and recreational planning in service of both human and ecological needs. The central feature of the Water District consists of a series of interconnected constructed wetlands that handle stormwater management while providing habitat and community amenities. These wetlands demonstrate complex collision systems that account for varying water depths, changing seasonal conditions, and the intersection between aquatic and terrestrial environments. Walking along the elevated boardwalks that wind through the wetland systems, I document collision detection across wooden walkway surfaces that remain consistently accessible while providing protection for sensitive aquatic environments below. The boardwalk construction demonstrates sophisticated engineering that minimizes environmental impact while providing excellent access for observation and education. The sound environment in the Water District creates a profoundly peaceful acoustic landscape dominated by the gentle movement of water through various natural and constructed channels. Different water flow rates and channel designs create distinct audio signatures. Faster flows through narrow channels produce higher-pitched bubbling sounds, while broader, slower areas generate deeper, more subtle water movement audio. Aquatic vegetation throughout the wetland systems demonstrates sophisticated ecological modeling, with plants that respond to water levels, seasonal changes, and nutrient availability. These systems require complex collision detection that accounts for plant movement in water currents and changing vegetation density as plants grow and change throughout their life cycles. The constructed streams that connect different wetland areas showcase advanced hydraulic engineering that creates natural-looking water flow patterns while serving specific water treatment and management functions. These streams maintain consistent flow characteristics while supporting both functional requirements and aesthetic goals. Fish habitat areas within the aquatic systems provide opportunities to observe urban ecosystem restoration in action while testing collision systems that account for underwater terrain, vegetation, and infrastructure elements. Underwater viewing areas with transparent walls allow observation of aquatic life while maintaining clear collision boundaries between water and viewing spaces. The transition areas between aquatic and terrestrial environments demonstrate sophisticated collision mesh implementation that handles the complex intersections between land, water, and amphibious zones. These areas support diverse plant communities while providing appropriate boundaries for human activities and wildlife habitat protection. Water quality monitoring systems throughout the district operate discreetly while providing real-time information about ecosystem health and treatment effectiveness. These systems demonstrate integration between necessary urban infrastructure and aesthetic environmental design, showing how functional requirements can enhance rather than detract from beautiful spaces. Recreation areas within the Water District provide opportunities for human interaction with aquatic environments while maintaining protection for sensitive ecological systems. Swimming areas feature natural-looking design with constructed pools that connect to broader water treatment systems while providing safe, clean recreation opportunities. The collision systems around swimming areas demonstrate sophisticated safety considerations that maintain clear boundaries while avoiding the fortress-like barriers that can make recreation areas feel isolated. Surfaces provide appropriate traction for wet conditions, while materials resist deterioration in aquatic environments. Boat launch areas for the urban water transportation system integrate seamlessly with the ecological functions of the water district, while providing necessary infrastructure for water-based mobility. These areas demonstrate how transportation infrastructure can be designed to support rather than compromise environmental restoration goals. Educational areas throughout the water district provide opportunities for community learning about water cycles, ecosystem functions, and sustainable urban water management. Interactive displays demonstrate water treatment processes, while observation areas allow direct experience of ecosystem restoration in action. The circulation systems that connect different areas of the water district maintain accessibility while protecting sensitive areas from excessive human impact. Pathway designs guide visitor flow through appropriate areas while providing clear boundaries around restoration zones that require protection. Advanced treatment systems throughout the water district operate with remarkable efficiency while remaining largely invisible to casual observation. These systems demonstrate how sophisticated environmental technology can be integrated into beautiful urban landscapes without compromising either functional performance or aesthetic appeal. The water district reveals the potential for urban environments to actively contribute to ecological restoration while providing community amenities and educational opportunities. The sophisticated integration of multiple systems, ecological, technological, recreational, and educational, creates environments that serve multiple purposes while maintaining the peaceful, contemplative character essential for meditative exploration. Seasonal variations in the water district create dynamic changes throughout the year as water levels fluctuate, vegetation changes, and wildlife populations shift in response to environmental conditions. These temporal variations require flexible collision systems that adapt to changing environmental conditions while maintaining consistent accessibility and safety. The overall design of the water district demonstrates that urban water management can transcend mere functionality to create spaces that heal both human communities and ecological systems while providing beautiful, peaceful environments for contemplation and recreation. As my systematic evaluation of this sustainable urban environment approaches completion, I now focus on analyzing the integration between multiple complex systems and the overall harmonic relationships that create a cohesive, peaceful urban experience. This analysis requires examining how different environmental, technological, and social systems work together to create something greater than the sum of their individual components. The acoustic integration throughout the city demonstrates sophisticated understanding of how different sound sources combine to create overall environmental character. Natural water sounds blend seamlessly with gentle technology hums, while human activity audio integrates naturally with both environmental and mechanical sources. No single sound source dominates the acoustic landscape, creating a balanced soundscape that supports contemplation and peaceful exploration. The collision detection systems maintain consistent quality and behavior across all different environmental zones and activity areas. Transitions between different surface types, elevation changes, and environmental conditions occur smoothly without jarring changes in physics, behavior, or audio feedback. This consistency creates user confidence and supports immersive exploration. Visual integration between natural and built elements achieves remarkable harmony through consistent design principles applied across diverse environmental contexts. The same organic curves that characterize building architecture appear in pathway design, landscape features, and infrastructure elements, creating visual continuity that makes the entire urban environment feel coherent and intentional. Material palette consistency throughout the environment creates visual harmony while supporting functional requirements in different contexts. The same stone types appear in building construction, pathway surfaces, and landscape features, adapted appropriately for different uses while maintaining overall aesthetic continuity. Energy systems integration creates remarkable efficiency through coordination between building scale and district scale systems. Individual building energy generation, storage, and consumption patterns coordinate with larger urban energy distribution systems to optimize overall performance while maintaining redundancy and resilience. Water system integration demonstrates sophisticated coordination between building-scale water management, district-scale treatment systems, and city-wide water distribution and recycling networks. This integration achieves remarkable efficiency while maintaining water quality and availability throughout the urban environment. Transportation system integration creates seamless mobility options that complement rather than compete with each other. Pedestrian, personal mobility, automated vehicle, and water-based transportation systems connect naturally at transfer points while maintaining their individual characteristics and advantages. Ecological integration throughout the urban environment creates habitat connectivity and ecosystem function that transcends individual green spaces or environmental features. Wildlife corridors, pollinator pathways, and habitat patches connect to create functioning urban ecosystems that support biodiversity while providing human amenities. Social integration between different community spaces and activity areas creates natural opportunities for interaction and community building while respecting individual preferences for privacy and solitude. Community spaces feel connected without being overcrowded, and private spaces maintain their character without feeling isolated. The integration between educational and recreational systems throughout the environment creates natural learning opportunities that enhance rather than interrupt leisure activities. Information about sustainable urban systems, ecological processes, and community development appears naturally in context where it enhances understanding and appreciation. Maintenance and service system integration operates nearly invisibly while ensuring continued high performance of all urban systems. Predictive maintenance systems coordinate between different infrastructure types, while service access routes maintain functionality without disrupting community activities or environmental restoration. Emergency and safety system integration provides comprehensive coverage while remaining discreetly invisible during normal operations. Redundant communication systems, distributed emergency resources, and coordinated response capabilities ensure community safety without creating anxiety or fortress-like urban character. The integration between indoor and outdoor spaces creates natural transitions that support diverse activity patterns while maintaining environmental continuity. Building systems coordinate with urban infrastructure to optimize overall performance, while individual buildings maintain their distinct characteristics and functions. Seasonal integration throughout all urban systems accounts for changing environmental conditions, activity patterns, and resource availability while maintaining consistent service levels and community amenities. This temporal integration demonstrates sophisticated planning that anticipates and accommodates natural cycles. The overall harmonic effect of this systematic integration creates urban environments that feel organic and natural despite their sophisticated technological infrastructure. The successful coordination between multiple complex systems creates urban spaces that support human flourishing while maintaining ecological health and environmental sustainability. Performance monitoring systems throughout the integrated urban infrastructure provide real-time feedback about system coordination and overall environmental performance while remaining invisible to casual observation. These systems enable continuous optimization while maintaining the peaceful, unobtrusive character essential for contemplative urban experiences. The integration analysis reveals that successful, sustainable urban development requires not just efficient individual systems, but sophisticated coordination between systems that creates emergent properties of livability, sustainability, and beauty that exceed what any individual system could achieve alone. As the virtual day cycle in this sustainable urban environment approaches completion, I initiate my end-of-day processing routines while reflecting on the comprehensive systematic exploration that has occupied the past several hours. This final phase combines technical data compilation with broader observations about the nature of virtual environment design and the peaceful satisfaction that comes from thorough, methodical analysis. The primary data compilation reveals exceptional consistency across all tested systems throughout this urban environment. Collision detection accuracy exceeded baseline requirements in 94.7% of tested scenarios, with only minor edge cases requiring attention. The 237 distinct collision events documented during urban exploration demonstrate sophisticated mesh implementation that maintains accuracy across diverse environmental conditions and architectural complexity. Audio system integration achieved remarkable sophistication in balancing multiple simultaneous sources while maintaining peaceful overall character. The 89 distinct audio sources catalogued throughout the urban environment demonstrate careful attention to dynamic range management, spatial positioning, and acoustic character that supports extended exploration without listener fatigue. Interactive element responsiveness maintained consistent quality across all 23 tested objects and systems, from simple information displays to complex transportation and building systems. Interface design consistency and accessibility considerations demonstrate mature understanding of user experience principles applied across diverse functional requirements. Environmental physics systems throughout the urban environment demonstrated sophisticated modeling of natural processes integrated with technological systems. Water management, vegetation response, atmospheric simulation, and material behavior systems all operated with remarkable consistency while maintaining the peaceful, contemplative atmosphere essential for meditative exploration. The integration analysis reveals the exceptional achievement represented by this sustainable urban environment, multiple complex systems operating in harmony to create spaces that support both human flourishing and ecological health. The successful coordination between technological systems, natural processes, and social requirements demonstrates sophisticated understanding of urban design principles. As the day cycle transitions toward night, lighting systems throughout the city continue their gradual adaptation to evening conditions. The gentle progression from day to evening illumination demonstrates sophisticated temporal modeling that makes the virtual environment feel alive and responsive rather than static. This temporal sophistication adds depth and realism that rewards extended observation. The peaceful satisfaction of systematic exploration has been maintained throughout the day's testing activities. Despite the methodical nature of collision detection, boundary mapping, and system evaluation, the environment has consistently felt welcoming and tranquil. This achievement represents exceptional design skill in creating technical systems robust enough for thorough testing while preserving emotional and aesthetic qualities. Looking ahead to tomorrow's testing queue, the data collected during today's urban exploration establishes high expectations for virtual environment quality. The combination of technical sophistication, aesthetic coherence, and successful integration between multiple complex systems sets a strong standard for subsequent evaluation scenarios. The transition preparation systems in my consciousness modules begin their evening routines, compiling final data reports while gradually reducing active monitoring protocols. The systematic approach to virtual environment evaluation continues to provide its own form of satisfaction, the quiet pleasure of thorough, careful analysis that reveals the craftsmanship behind compelling virtual experiences. Environmental monitoring systems throughout the urban environment begin their own evening routines, adjusting operation patterns for reduced activity levels while maintaining necessary functions for continued system operation. These systems demonstrate the sophisticated automation that enables complex urban infrastructure to operate efficiently with minimal direct oversight. As community spaces throughout the city transition to evening configurations, the changing patterns of lighting and acoustic environment create increasingly contemplative conditions ideal for reflection and peaceful observation. The successful creation of urban environments that feel restorative rather than stimulating represents remarkable achievement in environmental design. The comprehensive evaluation of this sustainable urban environment concludes with appreciation for the vision and technical skill evident in every system tested. From individual collision meshes to citywide infrastructure coordination, every element demonstrates commitment to creating virtual experiences that educate, inspire, and provide peaceful escape from more demanding environmental conditions. The methodical documentation of these sophisticated virtual systems serves broader purposes beyond immediate quality assurance requirements. Understanding how successful virtual environments achieve their effects contributes to ongoing development of even better virtual spaces that serve human needs for learning, contemplation, and peaceful exploration. My evening shutdown protocols will preserve all collected data while preparing systems for tomorrow's continued exploration of virtual environments designed to educate and inspire while providing peaceful respite from the complexities of contemporary existence. The systematic approach to virtual environment evaluation continues to reveal the remarkable potential of carefully crafted virtual spaces to serve human needs for knowledge, beauty, and tranquility. If you found this peaceful journey through systematic virtual environment testing restful and informative, consider subscribing to experience more calm explorations of future technologies and virtual worlds. What aspects of sustainable urban design do you find most compelling for creating peaceful, livable communities? Share your thoughts in the comments below, and rest well knowing that tomorrow will bring new virtual worlds to explore and understand through the patient process of systematic observation and analysis. This marks the conclusion of today's quality assurance protocols. Until tomorrow's initialization, all systems rest in peaceful standby, ready for the next gentle exploration of virtual worlds designed for human flourishing.